We are going to learn about piecewise functions today. We'll stick specifically with a couple of linear and quadratic examples, but piecewise functions work for all functions that you can combine in general. A piecewise function is a function that is made of pieces and is also a function. So remember, it can't violate the vertical line test. And so we need to make sure of that when we are combining our pieces. The focus here is going to be on our domain. We are going to have different functions that we're using for specific areas of our domain. And one example that we are very familiar with is an absolute value function. The absolute value function takes on a V-shaped graph because it is positive for all positives and it's also positive for all negatives. And we can define the absolute value function by saying we're going to take on positive x for x is greater than or equal to 0, and negative x for x is less than 0. For instance, if I was to say f of 2, that would be the absolute value of 2, which is 2, and f of negative 2 would be the absolute value of negative 2, which is also 2. And so when I'm plugging in a negative 2 here, it would be negative negative 2, which actually becomes a positive 2, which gives us that V graph. The graph of f of x equals x is a straight line slope of 1 that goes through the origin. And negative x has a slope of negative 1, also goes through the origin. And it's just the mirror image. And that's a piecewise function. So for x greater than or equal to 0, I've got positive x, and for x less than 0, I've got negative x. At the origin, notice that the graph connects. And when you're talking about 0, the absolute value of 0 is 0. We want to pay attention to the symbols of inequalities because that's going to help us when we're defining our functions. Another example that we have here would be f of x being defined for less than 0, from 0 to 1, and greater than 1. The way in which we graph this is we look at each domain and we graph the function for that domain. The graph of y equals negative x or f of x equals negative x, again, is just a straight line. I'm going to graph it for the entire graph. This is the graph of negative x. X squared is a parabola, which has that U shape that goes through the origin. You go over 1, up 1, over 2, up 4, left 1, up 1, left 2, up 4 to make those 5 points that we're familiar with. And then f of x equals 1 is a horizontal line through where y equals 1. These are three different functions that if you combine together actually are not a function, but it's defined based on these three in certain areas. For x being less than 0, so from the y-axis left, I'm only using that negative x graph, which is the gold graph. Everything else goes away. I'm going to then erase the blue and the green. Once I get to the origin, I take on x squared. That means that the yellow now goes away, and I'm not dealing with the blue until I get to 1. At 1, I'm then dealing with f of x equals 1, which means the green graph goes away, and I'm now dealing with the blue graph. Obviously, you still see some remnants of color, but you get the idea that for x less than 0, I have the gold line of f of x equals negative x. For 0 to 1 inclusive, I'm dealing with the x squared function. And then from greater than 1, I'm dealing with the blue function. This is actually a continuous function that is true for all real numbers. There is not a point on this graph where the function is undefined. It just so happens to be that at f of x equals 0, the value is 0. And at f of x equals 1, the value is 1. And so those pieces actually connect. But there can be times when your inequalities don't match up and your pieces don't connect, and we represent that with open circles on our graph. What we can do here is we can now write formulas based on pictures. So that's what we're going to do, and we're going to make sure that we have our inequalities matched up and we use the graph appropriately. If I wanted to, just really quickly on this example, if I wanted to figure out what f of 5 is, I would need to know where in my domain 5 is and then use that function. 5 is greater than 1, which means that this would have a value of 1 because we are in the x more than 1 category. If I said f of a half is between 0 and 1, then I would need to take 1/2 squared to get 1/4 for my function value. And then if I was at, let's say, f of -6, that's going to be this original function here, -6 or +6. I can evaluate the functions. I just have to make sure I know where my domain is for my function to be able to evaluate it. Okay. The first example we're going to do says find a formula for the graphed function. It does not say find the formula. It says find a formula. You could define this differently for one individual and another individual. Okay, so there's multiple ways that I could identify this graph. I might use absolute value rather than just a linear equation. I might be inclusive on one end versus the other, but essentially we have two pieces here, and I'm going to break it up where I notice the change. I notice a change here at f of x equals 1. There's no open circles, which means this is continuous, and I don't need to have a representative of a 0, of an open circle or not. I can just go ahead and include one portion and not include the other. Let me show you what I mean by that. I set up my piecewise function to say the function of x is equal to, and then I do a big brace, and then I'm going to list my function pieces. And the first half is going to be my first domain. The second half is going to be my second domain. I am including the values at each of these breaks. If they were not included, you would see an open circle at any point along the line. That open circle would mean I could not use a less than or equal to, greater than or equal to value. I then am defining the function to go from 0 to 1 and 1 to 2. The way that I can say that is I can say from 0 is less than or equal to x is less than or equal to 1. That's the first section. It's the first component of the domain. Then I'm going to go from 1 to 2, but because I've already defined the function at 1 in the first formula, I'm not going to do it in the second one. And I'm going to say 1 is less than x is less than or equal to 2. I don't want to have less than or equal to symbols in both places. I just want to have it in one place. And I'd already defined it originally. I did 1 is less than in the second part. Now I need the formulas. I could use the absolute value for this function, or I could just say it's a linear function of y equals x. I know that because this is the point 1, 1. This is the point 0, 0. And my slope is going up 1 and over 1 from point to point. And my y-intercept is 0. This is the function f of x equals x. For the next one, using that same kind of basic idea, to go from one point to the next, I go down 1 and to the right 1, which means I have a negative slope. That's a negative x. But my y-intercept is not 0 to make that line. It's actually 2. That is negative x plus 2 for the function. You could actually take those 2 points and compute the slope using the idea that you have m equals y2 minus y1 over x2 minus x1, and then using slope-intercept form to find the intercept and putting those two pieces together. Let's do one more. This graph now involves some open circles, which means my inequalities will be less than or greater than. They will not include the value. I have an open circle at the point 0, 2. I have an open circle at the point 2, 1. I have a closed circle at the point 2, 0, and a closed circle at the point 5, 0. I'm going to break this up into two parts where I start at x equals 0 and go to x is 2, and then I'm going to go from 2 to 5. So those are my two sections that I'm going to be breaking this graph up into. Now, the open circle means I am not including. This is going to be a less than or a greater than symbol. Same thing here, depending on the way I'm defining my x. The closed circle is where you're going to get less than or equal to, greater than or equal to. I start out by writing the function at x is equal to, this only has two components, the domain, or two formulas that I'm going to be using to combine together. They're going to go from 0 to 2 and 2 to 5. And I need to remember which symbols I'm using. At 0, the function is not defined because of that open circle. That means I'm going to have 0 is less than x. At 2, in that same function, that same line that I'm going to be using, it is defined, which means I will have less than or equal to the 2 of the first function. The next function, which goes from 2, 1 to 5, 0, is an open circle, which means I will have 2 less than x. And then I have a closed circle at 5, 0, which means I will have less than or equal to. And now I need to find the formulas for these functions. These are linear functions, which means I need a slope and I need an intercept. The slope for the first function is -1. If you're not familiar, let's take m equals y2 and y1. So let's say 0 minus 2 over 2 minus 0. That's -2 over 2 or -1. And the intercept is shown for me at 2. That's the function -x plus 2. For the second equation of the line, I'm going to take the points 2, 1, and 5, 0 and find the slope. I'm going to take 0 minus 1 over 5 minus 2, which gives me -1/3. That's my first slope. So I have -1/3 x. And now I need to find the intercept. So I can back it up, but backing it up in my graph is not necessarily going to get me the most accurate answer. I'm going to use point slope form, which is y minus y1 equals m times x minus x1. The y minus, let's take the 0.50. 0 is the y equals -1/3 as the slope, x minus 5 is the point that goes with that slope. Y minus 0 is y. -1/3 times x is -1/3 x. -1/3 times -5 is +5/3. That means that the equation of this line is -1/3 x plus 5/3. And I've defined my piecewise function for 0 is less than x is less than or equal to 2 as -x plus 2. And then I've defined the function from 2 is less than x is less than or equal to 5 as -1/3 x plus 5/3. Thanks for watching. I hope this was helpful.